So welcome everybody. Thank you for coming to the final lecture of Academy of AI on generative adversarial networks. I'm going to go through the theory and then go through an implementation of this. So let's get started. So the motivation for GANs, firstly. So I'll explain what we're talking about here as well. So all the models that we've seen so far have been predictive models, predicting, say, a classification or the coordinates of a bounding box or some continuous numerical answer. But it would be awesome if we could have good generative models. And that's models that can create new things. So the strong and long-term motivation for generative models, of which GANs are state-of-the-art currently, is thinking ahead and imagining AI that could do things like compose music, or to write fiction, or to make films, or to even write new software, or create new business or research ideas generatively. This is not prediction now. And all of these, which I guarantee will be done, will require generative models. And so here's just some few examples of implementations of GANs. So these are generative models that have, in this case, created all these photorealistic photos of people's faces there. I just put that image there to represent, like, they've done the same thing for music. We're going to be working with images today because it's obviously nice and visual, but the same kind of thing applies to other types of data, audio, video, text, etc. Super resolution is another one, so taking a low resolution image and upsampling it and then inferring the resolution in between where you've upsampled. A really cool application using what's called a cycle GAN, or at least one implementation of it, is doing analogous style transfer. So where you have analogous data sets of different things, and then transferring the kind of the style between them. So here you've got black and white to color, day to night. Another cool one is like you can do like zebras to horses and just like apply the style onto the horses to make them zebras, vice versa. And this kind of thing, similar to kind of super resolution, but in this case like sketch to actual object. And so there's these sites which I thought we should have a look at as well. This person does not exist. So this is a site where it just shows you images, and these are all GAN-generated images. So these aren't real photos of people. And sometimes you can spot the artifacts of and tell that it's a generative image. Like there, you see there's this weird blotching, for example. I don't know how to move on. But anyway, there's so that just prompts you new photos of generated images. Again, like you can see like some weird artifacts in some places where it hasn't quite captured it, but otherwise it's like that's a photorealistic picture, and if we weren't looking at that with GANs in our head, we wouldn't know the difference. So that's one other thing. I don't know if there's a good website for it, but so this is something called Big GAN, which is a GAN they trained on a huge data set, and it's got massive capacity to represent really complex image generation. And these are all the kind of things which is generated, but this is trained on just a massive data set of not a particular type of thing. So the images which it can create are not specifically from one category, but are from all different kind of things. And there's a really cool thing you can play with where you can basically move through the feature space of the inside of the model and basically zoom around this latent space and see what image is generated from those low-dimensional features, which is really cool. So just things to check out if that interests you. Okay, cool. So we're motivated now. But yeah, what actually is a GAN? So GANs are state-of-the-art generative models that can use unsupervised data to learn to create new content which comes from the same distribution as the data which it's seen before. So think back to those examples I showed you. In the case of music, what it's done is it's listened to a load of songs, it's analyzed the distribution from which those audio tracks come from, and then it's tried to basically implicitly represent that distribution and sample from it to generate a new instance of something which should be representative of that data. And so the way this is done is by taking two neural networks and basically battling them against each other so that they're both trying to optimize for different things in a zero-sum game. So as one gets better, the other gets worse. Let me show that now. So one network, the generator, is trained to transform random noise into realistic-looking, sounding, whatever, data. Into realistic data that represents the training set. And then another network, called the discriminator, is trained to classify data as either generated or real, right? And so we have this diagram. So we'll walk through this. But that's basically a simple GAN. We start off with, on the left, that Z is a vector of random noise, okay? And what we have is this thing G, a generator, which we're going to use a neural network to try and represent a transformation from random noise into hopefully realistic looking fake data, okay? So this is one of the functions that we're trying to learn. This is one part of the model. And then we also have another part of the model here, which is real data. So this is our actual data set X, and this is our predicted X hat. And so taking those two things, what we're going to do is we're going to feed them both into a discriminator over here, switching between them every now and again. So switching between real data and fake data, and then have the discriminator, which we'll use another neural network to represent, try to output from those inputs, either real or fake. What it'll try to output is a classification of whether this is a real or a fake example. And then we'll feed that into a loss function, and then that will evaluate how bad the model as a whole thing is performing, and then we can find out how to improve the parameters of both the generator and the discriminator in different ways, such that they try and do what is going to be a good job for them to either generate fake images or classify real or fake images. And so like another a more intuitive interpretation of this is you can think of it like the art forger and the detective. So you have the generator, which in this case would be the forger, trying to create fake art or whatever, fake money, and then the discriminator, the detective, looking for trying to identify the real or fake money. And so as to start off with, neither of them really know what they're doing. Maybe the forger learns something and he can create fake money more easily. He finds a quick way to do it. But then the detective will find a way, like, okay, it's the material. I've noticed a different material. I've noticed a different pattern, whatever. He learns that and then combats the generator being able to pass that off as legit. So it gets caught out. And then after that, the generator has to evolve again further, past that simple strategy which the discriminator has already seen through, and try and figure out a better way to make more realistic versions of whatever they're trying to recreate. Okay, is that at a high level understandable to everybody? Marcus?
So the generator want a higher loss function?
We'll get onto loss functions in a sec. Yeah, They're actually two different loss functions, but you can train them jointly. So we have the generator trying to represent transformation from some random noise into some realistic looking data. And we have the discriminator trying to detect the fakes from that. And this is just alternating between these two at some different frequency, potentially. So how do we actually train them? That is a joint loss function of the discriminator and the generator. So we'll walk through that very slowly now. So what we have, just breaking this down in here, we have this term here, d of x, right? This is the discriminator looking at a real example. And so that's going to output some number between 0 and 1. And we hope that, well, the discriminator hopes that it's closer to 1, right? Because he's trying to classify whether that's real data. And then taking the log of that, I'll draw this out quick. Yeah, taking the log between 0 and 1 is going to be a monotonically decreasing or increasing function, depending how you look at it. And so we have that log of a number between 0 and 1. And the generator, sorry, the discriminator is trying to maximize that, right? They're trying to maximize that part because they want to always be predicting 1 when it's a real example. So then, and then we're going to, basically find the average of that over the whole true data distribution. And then we have another term in the loss function, which is, so yeah, breaking that down, we'll go through this, like I pointed out. So the average over the real data. And then over here, we have g of z, right? So the generator has acted on z, the vector of random noise, to try and produce what should be a realistic looking image, right? And then we're passing that image, that's x hat there, into the discriminator, which will then output a number, again, between 0 and 1, where that is a confidence that this is a real example, okay? So, and then we're taking that away from 1 in this case, right? So, so yeah, and then the other one is going to look like that, right? Well, that's asymptotic at 1. And this means that as the discriminator, I think, yeah, so this is saying, is this real? Is this fake data real, right? And when the discriminator thinks this fake data is real, then this will be a 1, and this whole term there will go to 0. So then you have log of 0, and obviously that's very low there. And so then we're trying to maximize this whole thing with the parameters of the discriminator and minimize it with respect to the parameters of the generator. So we'll break it down in a second, it gets more clear as well. So basically, this time over here, we have the generator wanting the discrimination of what the generator outputs to go to 1, okay? So the generator wants this whole thing to go to 0, and so this whole term will be minimized with respect to their parameters. But the discriminator wants d of g to go to 0. And so that's here where they want, so that would be, 1 minus 0, you'll output 1, and this will be maximized, which is what you have, which is what you're trying to find there. So that's the joint loss function, but it's more clear and simple with the separated out versions. So we have the discriminator loss, like this, which is basically is this thing, but you don't have to worry about the argmaxes there. So we're basically trying to maximize this thing or minimize the negative of it. So yeah, with respect to the parameters of the discriminator. And then we have the generator, which is a simple loss function, which is trying to, then we're going to try and minimize both of these losses, right? So then we're trying to minimize the expected log, 1 minus log likelihood of the discriminator being correct. Yes. So yeah, okay, I think I'll point this out right now. Okay. Yeah, well, okay, just again, this is the, fake data. Do I think the fake data is real? If I do think the fake data is real, then this is going to go to 1, and then this will be 0. And so fits in with that loss equation there. But this looks like this, basically. So this is this one on the right-hand side. And that's fine. So optimizing for both these things will, should theoretically try and make the generator produce as realistic images as possible and make the discriminator maximally kind of unsure as to what these are. So when the training stabilizes, what you have is the generator loss will plateau down to some value, and the discriminator loss will plateau up to 0.5, where for every example, it just has to output a 0.5 because it's indistinguishable between real or fake data. Okay, so we have that, but there is some problems with this. So the way this loss curve looks is d of g of z, right? This is basically when the discriminator is classifying the fake data as real, this will be 1. Okay, so we'll have a value, up this far. Sorry, up this far. Yeah, my bad. Up this far end of this curve, right? So when this is high, when it's close to this end, that's when we have a good model, right? And that's when the gradient is high, right? And so because we're doing gradient-based optimization, that's where we'll be updating our parameters faster, by more, and hence maybe learning faster. But the problem is when we start, this is going to be low, right? At least, so the discriminator should be able to distinguish between real and fake examples, because the fake one will literally look like random noise, and the real ones will look like from very complex distribution. So to start with here, we have this low gradient, and this means that we'll be learning slowly initially. So instead, what we can do is flip this loss function. So I'll show you that equation in a sec, and have a it's there even. So instead of using this one, we can instead of maximizing the probability of the discriminator being wrong, we can minimize the log probability of the discriminator being right. So basically the same thing, just different formulation of it. But now the loss curve has a high gradient to start with, and so when we initialize the model, then what we'll have is we'll be learning quickly to start with. Is there any questions? About that?
Actually, so at the end, in this first equation, just substitute the last term with the one that's better.
So you're like that's what you want to optimize for overall, but we're not going to use that one. We'll just use 2 different separate ones. Okay? Yeah. So just keep it simple. It's easy to understand that way as well. Yeah. Cool. Any other questions about this? That's like the full GAN architecture and training algorithm. Okay, cool. So we're just going to do what we've all done before. We're going to build that model, and then we're going to make these loss functions, and we're going to give it our data and optimize that. Okay. So yeah, now just a few more things to mention about like how we're going to implement this and how the training is going to work. So the random noise that we're going to generate is the random noise is a low-dimensional vector, and we want to generate images from a vector. So what we're going to do is we're going to reshape the vector into a tensor, so it's like a very low-resolution stack of images. And then what we're going to do is try and do basically the inverse of convolution. So with convolution, you're having your input get smaller as you apply that transformation. But we're going to do something called transpose convolution or up convolution, where the input is actually expanded. So we're going to have a low-dimensional representation and then try and expand it to a bigger one. So yes. So we've seen that, right? Where we have something like an image, and we convolve over it with a bunch of different filters, and each of those, each output of the filter is 1 channel thick, and you have a stack of them in the next layer. And then you convolve over those ones, have another stack of more complex activation maps on the end. That was convolution. So in that case, we're downsampling our data to get a lower dimensional representation of it, combining features along the way, such that the features in the later layers should have a more meaningful representation. Okay. But can we do this? Is the thing. So we want to do up convolution or transpose convolution. So I should put an animation there. So yeah, what this looks like is, so say we have some just vector. This is the vector form, this is the tensor form. Say we have some vector, and we have a filter, which we're going to do up convolution with. Basically what we do is we weight every value in this filter with the input, which we're on at the moment. So we'll take that filter and we'll we can't quite drop it over the image as we did with convolution, but we can kind of project the input point which we on the image onto that filter. So multiply this by all of these, and then those go into the very first position in our output. Okay, and then we'll stride our filter from this position along 1 to this position, and then we'll do the same and multiply this this number here by every value in our filter. And these are learnable weights. These are just parameters of a transpose convolutional layer. And then we'll take those outputs here, which have the B in, and so we just strided again. We strided 1 in our output here, and then we've added them where they overlap. Okay, but here we've taken a 2 vector into a 4 vector in a learnable way, right? So these will all be parameters that we can try and learn using the techniques which you've seen many times before. So how does that work in the tensor form, or if we want to up convolve an image? Yeah, looks just something like that again, and then we have a matrix of weights. We take that value, multiply that value by every number in this filter by that input value, and that gives you the first term. At least the first term in this layer, in this region of the output here. Okay, so we've just projected that input onto each of these weights and then dropped onto the output there. So that's all the WAs in this part, and then we just slide that filter over to the next position with the stride 1, and then multiply all the values in this filter by this B, and then drop them into the output there as well. And if we have any where there's already been values like that, like these ones here, then we just add them together. Okay. Any questions about that? Cool. Yeah, it's kind of weird to think about, but it's just sort of like an inverse convolution in the opposite direction. Okay. So that's what we're going to use to upsample our low-dimensional noise vector into some hopefully realistic image, right? And we're going to use another technique, basically on all the layers all the way through, because it really stabilizes training, and GANs are notoriously difficult to train. We're going to use batch normalization. So I think I gave kind of a quick run-through explanation of that before, but we should do it in more depth because it's quite a critical technique. This is a technique which is, like before this, it was like you couldn't really train super deep models. You would leave the model and then just come back, and it may have just diverged over time, and you just can't find a solution. What batch normalization does is basically puts a stake through the model and holds it all together in one nice stack instead of it diverging at different layers. We'll see that here. So activations should represent the presence of some perhaps complex feature in the input data, right? You'll know that by now. So it would be useful if they were distributed about some mean value, as we'll explain here. So if we had every activation, every neuron in our neural network representing something meaningful, then we could say that, like, okay, is it an extreme, does it have this feature a lot? Is it an extreme example, or is it a less, or the opposite extreme of this kind of example? But in the middle, you'll find that, if there's an average value for how present this feature is in every example, they'll cluster towards the middle, and then we can see, okay, within what percentile does this new example express this feature? Okay. So if we wanted our activations to follow some distributions like this, then we can force them to by just normalizing them, and that will be done by subtracting the mean and then dividing by the standard deviation, right? So then we'll put all of our output activations into some Gaussian range like that. So what does this mean here? We have what we're going to output is our normalized activations in layer K of our model, right? The way we get them is by taking the activations in that layer, every single one of them, and then subtracting the the mean of the activations in that layer, and then dividing by the standard deviations of all the activations in that layer. So there's the original activations, the mean of the activations, and the standard deviations. Those are the mean and standard deviations across a batch. So you have a batch of examples going in, and then each of them would give a particular activation at every different point within that layer. And then throughout the whole batch, you would find, okay, what's the mean and what's the standard deviation of those things. Subtract the mean, divide by the standard deviation, and normalize the activations for everything in that batch. Okay, is that clear? All right. However, there's a problem with that. Because if our activations are all centered around 0, first thing is that some of the activation functions that we're using, like sigmoid, for example, is kind of linear in the middle. And the whole point of having them was so that we could introduce nonlinearity into our models. So if we have within like the less than 90th percentile here, we have 90% of the results fall within this green bracket, then they're going to fall within this range, and that's basically a linear layer. So then we're just losing capacity from our model, because we won't be able to represent as complex nonlinear functions if we're just using the linear part of this input here. So that's one problem if we normalize them and center them around 0. Okay. And there's another problem, which is that activations that might be important in later layers might require information that indicates not whether the input had below or above a certain mean presence of some feature, but whether it was like above some threshold of extremity of representing that feature. Like, am I definitely sure it had that feature? Maybe that's what really matters to some later activation that we'll have. So yeah, like say this feature only matters if I'm 90% sure of it, something like that. So what we want to be able to do is to, after we've normalized these activations, is shift them and scale them so that we can basically only put basically shift them so that we can, when we pass them into an activation function like a relu, for example here, if this is the presence of some feature, and this feature is like, okay, it's an important one, but it only matters when it's really extreme. If we can shift this distribution over to here, such that only like 5%, the top 5% of examples exhibit this feature, they're the ones which remain a positive value for this activation. Then we pass them into the relu, the most common activation function that we're always going to use. Only the positive parts give any output. So in this case, we can kind of switch on or off whether that's the point of relu, is to switch on or off whether we want to represent this feature. But now we've normalized them so they can represent the presence and the degree of extremity of features, and we can just basically pass on information from most important ones, or from whatever proportion of this that we want to. Okay. So this could be something like, this feature has to be above some threshold where it's like, okay, I'm really definitely sure that it's got this thing that might matter to something later. Okay. So to counter those two problems, we use not just that standard normalization, but the actual core of batch normalization, which is to introduce 2 more learnable parameters per activation. So we have the batch normalization equation, which is what we did before. So we took every different activation in a batch, we subtracted the mean over that batch for that activation, and then divided by the standard deviation for that activation. Now what we're doing is we're multiplying by some learnable parameter, gamma, and then adding some beta, just the linear transformation. So nice and linear, easily differentiable, and hence learnable. Nothing more complex than what we've done before. So what do these do? The gamma here can take the activations which come into a layer and flip them or scale them. I'll show you in a sec. And the beta can shift them. So for example, we got some distribution where it's like, okay, all the top 95 percentile values for that activation, they're being passed on. Say if we give that into a ReLU, maybe we only want the bottom 95. In which case, if this were -1, then we could flip that. Okay, so that's one power of batch normalization. Can also scale it like that. So if we did a scale and a shift with this, then we could basically spread out the representation and give more distance between different activations. Not so intuitive, that one, but and again, similarly to like how the flipping can occur, then we can shift this distribution back and forth so that certain parts of it contribute more or at all to any next layers. Okay. Okay, cool. So those are the slides. Any questions? Cool. All right. We're gonna implement it now. So let's have like a 5-minute break or something. Go to the bathroom, get a drink or something if you need to, and I'm just gonna remove the code from the slides so we can implement that now. Yes.
About my project.
Yes. You didn't fill in the thing?
No, I didn't because it was February. I sent you an email because it was like 17th of February or something. Yeah. So I wasn't really sure.
Oh yeah, did I not change the date on it? No. Yeah, it's like every Sunday. It's fine.
Yeah, I have a question.
Go for it. Yeah, what's that?
I'm doing a project.
Yeah.
I still don't really know what's going on, but I wanted to see if it was like possible. So what I'm trying to do is kind of map out the electrical signaling between cells, and kind of, and I'm trying to use the free energy principle so that to kind of make the cells into a statistical model and say like they're all trying to act to minimize free energy, maximum. Anyway, it's one of those things. And
yeah.
do you think I could use so last week I thought the long short-term memory was good because it kind of shows all the communication between all these different layers.
Yeah.
But is there a way to combine that with this one?
Yeah, definitely. Just gotta put it all together, but I don't exactly know how or why.
Because because I'm trying to map, and well,